Yaskawa.
You're watching the PLCopen Basics video tutorial series. This video shows how to use the enumerated data types, MC direction, and MC buffer mode. Hi, I'm Matt Pelletier. Up to now, we've been ignoring the MC direction and MC buffer mode inputs on the positioning blocks. So follow along with me, and we'll show the rotary axis how to take the shortest path back to position 0, and we'll create a blended move for the screw axis to follow. So first of all, what is an enumerated data type? The most simple definition is that it's a name for a number. Where there are several selections available for a certain option, you can either give them numbers, 0, 1, 2, 3, etc. Or to make it more descriptive, you can give each of those options a name. So for example, if direction would have an integer 2 connected, that's not quite as clear as seeing the whole term MC direction pound negative direction. It's very clear then that the absolute move will move in the negative direction. Makes it a lot easier to read and reduces then the possibility for mistakes. Now here in our code, I've got the positioning POU and I've moved down to the absolute move. And we always could have looked at the help for this. You know, you hover over these and it says data type integer, but if you right click on it, you'll see more details. Look at the help. And scrolling down to the help, you'll see that there is MC direction and MC buffer mode with the correct spellings of the literal values for each of the options. Also notice that this is a hot link here to another part of the help, both of these here. And if you click on it, you can get more details on what this enumerated type means. But how does your controller know the definition of the data type? Well, that's going to be in the user library called the Datatypes toolbox. You can always see the details of any library, such as the Datatypes toolbox, by going to the Libraries tab and expanding to the data types. This one's in Motion Block Types. And scroll up toward the top. And here you see all of the different enumerated types. And we'll be focusing in this class on MC buffer mode and MC direction. There are others related to PLCopen and some specifically related to Yaskawa functions. Let's look now more closely at MC direction. And this may be a familiar concept to you if you've worked with rotary loads before. But while a motor obviously has only 2 directions it can turn, when you're doing absolute positioning of rotary loads, there's in a sense 4 possible directions. And they're listed here. There's of course positive and negative, but of importance is the shortest way, because you can go either direction to arrive at an absolute position, because the position modulates at a certain point in the rotation. In this case, we're saying it's at 360 or 0 degrees. And so that means that one of the 2 directions is the shortest way, the other way is the longest way. And another option is to just keep going the current direction rather than reversing. Go the current direction of whatever the previous move had been to arrive at the final absolute position. So this concept of shortest way and current direction really only applies to this specific case of absolute positioning of a rotary load that's been set up with this modulus. And MC direction does not apply, therefore, to any of the MC relative moves, or if you have a linear load, it still doesn't apply. There's only one way to get from point A to point B if you're working on a linear system. And one block we have not used in this class is called MC move velocity, and that one does take the direction as either positive or negative, and the other values are ignored. And over here in PLCopen Plus, MC move velocity help shows that it does have the direction input. And although these same options are listed, the only logical options are, in this case, positive and negative. I'd mentioned that the code would show the word clearly, shortest way, positive, negative. And this literal format is something that you should be used to in IEC. Compare such as unsigned integer #1 or lreal #1.0. And so MC direction pound shortest way follows that same format, which is the data type, pound, and then the data. The easiest way to handle these then in your code is to open up the help with a right click and then copy the option that you want and paste it in as the variable name. This way it's a lot easier to avoid mix-ups due to just spelling it wrong or forgetting the underscore. So how about let's put this to use right now in our code. We do have a rotary axis that's set for degrees. And you may recall back in the hardware configuration that not only is it named rotary, but we have the machine cycle set to 360, the user unit set to degrees, and the load type set to rotary. This is all in the hardware configuration. But this is the only reason that it will work in our system. Just to verify where that is very quickly, remember the hardware configuration and the rotary axis. Configuration tab shows that data. Now the screw configuration tab does not have a machine cycle because it's a linear load type. And so we would not be able to do rotary shortest way on this axis. So if you're using the MP2600 for this training, you may want to temporarily set this machine cycle to 360 and set the load type to linear, since the MP2600 has just the single axis, which up to now we've dedicated as the linear screw axis. Please connect to the controller after you're online, then go to the screw, change the machine cycle to 360, the load type to rotary. Can change the units then, will appear degrees. Then while online, you need to save and then reboot. So I'm not going to do that because I'm using the MP2300S IEC and we'll just use the rotary axis that already exists. Okay, so follow along with me. This isn't too tough. We've got the move absolute for the rotary axis and we want to put the direction on here. So I'll right click the help, scroll down, got MC direction shortest way. I can copy this, Control C or right click and copy. Now open up the direction and just paste that in. And that's it. Before we download this change, let's go into debug mode and let's take a peek at what's going on here beforehand. We'll start it off. And I'm looking at the right hand motor. It's going out and it comes back, doing a 270 degree move out and then back to 0. So now we'll make and download this change here. Close the resource and back to debug mode. I think we'll see that this is different right away. So it moves 270. The other motor moves. And now it moved only 90 degrees back to position 0. So absolute move, it looks like it has the position 0 right about here, since we never did 0 that one up to the top. So you see it's finding the shortest way back to position 0. Enumerated data types can also be used as a variable. And for example, here I've got one called move direction with the data type MC direction. And then you can set that variable in your code. Here I'm using a move function to move that positive or negative direction into this move direction variable. And that way you can change the value of the direction live as the program operates. However, there's some limitations, which are that the data type is not. However, there are some limitations which makes this a little bit more difficult to use. There's data type detection. And I'll show this here in a minute. When you go to make the variable, it won't detect that it should be the enumerated data type. The debug display has some limits, and you can't really see the value of a variable live in the debug display. You can load it within the program, which usually would be structured text. So I will show how that's done on the screw axis. This won't make any difference to the operation of the screw. But I can make a variable called move direction. And curiously, it only gives us integer, but never fear, just click OK. When you come back in here again, you can then choose MC direction. Now you cannot give an initial value, but you can click OK. And then elsewhere in your code, you could put the changing value of move direction in here. If you're not going to change the value, then you might as well use the literal like we did down here and just leave it fixed at whichever direction you intend to use. Another input that many PLCopen function blocks have is called buffer mode. See this one here, buffer mode. And you can look at the help for this also. And you see that buffer mode. And basically what buffer mode means is that if you apply a buffer mode to move number 2, it can wait for move number 1 to be done even if it's already been executed. It will wait for the previous move to complete, or you can even blend into the previous move. So this is exactly what you need to have some type of blended multi-speed move. And often this is used for registration applications where you're waiting for some type of input to determine an exact remaining distance. Now in our project, I'd like us to make a very simple implementation of blended moves using the buffer mode. So at the top of your positioning POU, you can take that first move relative into the screw, and as soon as that is active, you can execute a second move on the same screw axis. So set a different distance and a different velocity for the second move so you can tell the blending has taken place. Also set a slower XL and decel. I'm using 1000 instead of 360,000. And for buffer mode, I'm going to recommend that just for testing purposes, rather than creating an enumerated data type literal or an enumerated data type variable, let's leave it at the default integer. And this way you will be able to change that value of that integer and experiment with the different buffer modes without recompiling your code every time. Additionally, I'd like us to hone our skills on the logic analyzer, which we do cover in the IEC Basics video tutorial series, and there's a separate e-learning video on it also. But see if you can use the logic analyzer. I'll have to add some code here to read the speed and to trigger on the rotary absolute done. That's the last bit in the sequence. And here's a little picture of what you can use for the logic analyzer. And you'll be able to see then that the velocity blends from one to the other. Okay, so please use these 2 pages to create the code and create a trace using logic analyzer. And I'll show you my solution after the exercise. All right, I hope you were successful, and here's how we do it. Up here at move relative, I'm going to put in another MC move relative, so you can squeeze it in here. MC move relative. This is for the screw. And active will execute it. Now I'm not going to use the same distance. I'm going to make a new one called distance 2 with an initial value of -60. Velocity I'll call velocity slow. Velocities are always positive. 90. And for acceleration, we'll just use a literal here of real pound 1000.0 and copy and paste that on there. And now the star of the show here, buffer mode. I'm going to call it buffer mode _int. And I'm not going to change it. I'm going to give it an initial value of 1, which is buffering. Now, if I was developing, I would probably try this out first, but I'm pretty confident I'll do it right. And I'm kind of breaking away from the best practice layout here, I do admit that. But I want to get the screw's velocity from an MC read actual velocity. That's in PLCopen Plus, MC read actual velocity. And I'll just put it down over here to the side. Often we'll put these in a separate POU. I'm just leaving them in the same POU here. So like the others, you can just simply put a true on here, and let's give this velocity an output name. And that was going to be velocity _screw. And we'll download those changes. Okay, now I'm online and looking at the motion. And I can tell that this final position is not what it used to be. I can go back to 0 on the left, but it's not ending up at 270. It's ending up at 60 degrees beyond that. So that confirms. And visually, I think you can somewhat get an idea that it's slowing down. If you'd like to, you could reduce the velocity even further, maybe to 45.0. That makes it even more evident. But good practice, visual is usually not good enough, and this is why I want us to use the logic analyzer here. We can very simply right-click on the velocity, click Add to Logic Analyzer. You don't really see anything happen right away, but just have faith. And here's Done Rotary Absolute, and I'll add that one to the Logic Analyzer. I'm using this one because it pulses on when the whole sequence starts. So we can use that one to trigger the Logic Analyzer. Now let's go see some of these variables that we added to the Logic Analyzer. And that's under View, Logic Analyzer. And sometimes it looks like nothing happened. That's because it's likely to be in a very small docked window. I think by default it ends up at the bottom right. Here's the trick. Right-click on this title bar and uncheck Allow Docking. It may still be very small when it undocks, but you can easily make it larger. And then all the setup can be done here on this Configuration Resource tab. Right-click on it and choose Trigger Configuration. These buttons are also up here. There's a Logic Analyzer panel. Sometimes comes in handy. And now we'll set it up. And the first thing I think about is what is the trigger condition? What will start this data to be captured? And let's look at the Done Rotary Absolute having a rising edge, RE. So when that bit turns on, that's this one here, goes from off to on, then it'll take the data. Pre-recording means let's have some cycles before that time. Buffer a few data points before, and maybe 50 is good. And how about 300 data points after the fact? And synchronous with the fast task, because if you notice here, the variables are also in the fast task because this POU is running in the fast task. So click OK, and with the motion running, you can then click Start Recording, F11. It's up here too, red button. The data's uploading. And here it turned out to be the blue channel. This is my speed at -180, and then the speed here at 50. You can take out a cursor and get a measurement of that. If you want to. And here we're seeing how buffer mode number 1, it's waiting for this high deceleration move to complete and then doing the next move right after it. Looks like I could have had a little bit more time here, a few more samples. But now we can very quickly make a change to this code in debug mode. Let's change that from a 1 to a 2. And you can hit record again. And you can see this time it did the quick deceleration, but it didn't actually stop. It's somewhat blended. The resolution is kind of choppy, and the tuning may leave something to be desired, but you can see it's basically blending into the lower speed with the deceleration rate from the previous move. Try buffer mode of 3. Hit record. With buffer mode of 3 here, it's very easy to tell that the second slower deceleration is being used. So if you're curious on the other modes, you're welcome to go ahead and try that. You could try changing it to a positive distance seeing what happens when you cross through the 0 point. All this is explained in the help under MC buffer mode, and there's several different timing diagrams given that show how this is supposed to work. Thank you. That's enumerated data types, MC direction, and MC buffer mode put to use in our program. This will be the last development that we do with this project in this training course. So you're free to take this as far as you want to go. But I am going to save this off as a zip. Call it 08 enum DTP. Zip it. Thank you. We'll see you in the next video.